The Einstein Hilbert action formulated by David Hilbert arrived at the action principle motivated by variational formulation of physical theories. It provided an elegant derivation of Einstein's field equations using the least action principle. However, this beautiful mathematical formulation is fundamental, beautiful, simple, and carries a profound significance in our understanding of the universe. In this video, I will explain some of the grand insights of this formulation which reveals the simplicity and gracefulness of nature. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the Einstein Hilbert Action Explained. First of all, let us understand by the definition what is Einstein Hilbert action. Well, if you go by the definition, then the Einstein Hilbert action tells how gravity works in the framework of general relativity. By using the action, we can determine how the curvature of space-time is influenced by the presence of mass and energy. And when we say vary the action, which is the method in physics to find equations from a given principle, we end up with Einstein field equations. So if we take the two sides, one on the left hand side we take the Einstein Hilbert action, and on the right hand side we take Einstein field equations. So definitely from Einstein Hilbert action we can move to Einstein field equations. However, from moving from Einstein field equations to Einstein Hilbert action, well, I would say a little bit difficult and not always possible. The reason behind is that this is much more fundamental because it is a part of the Lagrangian formulation of physics, where the idea is to find the action and it is used to derive the equations governing the system. Where Einstein field equation is primarily based on what are called 16 nonlinear partial differential equations, which describes how space-time curvature is influenced by energy and matter. Now, just to tell you, when we will proceed with this video on Einstein Hilbert action, there are many different formats, types and styles in which this particular equation is written. So we will stick to one particular style, and I will also explain why these different types of equations are there. So from here, what we can now understand that from Einstein Hilbert action we go to EFE, or Einstein field equation, because this is much more fundamental, which is based on the Lagrangian formulation, which depends on the action principle. Moving on, what we see is that Einstein field equation is a set of nonlinear partial differential equation. That means if we get this kind of a curvature, so EFE, or Einstein field equation, actually describes how matter and energy influences the curvature of space-time. And the tensor which is responsible for creating the curvature is what? The stress energy momentum tensor. So we can say that the stress energy momentum tensor, which is given by the T mu nu, actually causes the curvature. Whereas on the other hand, the basic fundamental metric tensor, which is denoted by G mu nu, which contains all the information about the geometry of space-time. So from here we can see that definitely Einstein field equation is a local equation and is rooted in classical field theory, because it is coming basically from the field theory or the classical field theory equations. So the stress energy momentum tensor, which is causing the curvature, and the G mu nu, which is the metric tensor, actually contains all the causal structure of space-time. On the other hand, if we look into Einstein Hilbert action, you see that it is a scalar quantity. A scalar quantity in the sense that the EFE are derived from the variational principles, but they are directly focused on how space-time evolves, but this is not. So this is, I would say, Einstein Hilbert action is much more global description of general relativity, and it encodes the dynamics of space-time geometry with the interaction with matter through a single scalar action. Now, you might question that why it is a scalar. We will come to that, because in order to get a kind of a theoretical formula where it won't make any change, I mean to say, if you take any arbitrary point in space-time, then the formula or the formulation would be remaining invariant. We need a scalar, because the vector would change, scalar would be remaining invariant. So from here what we can say that the action approach connects general relativity to the broader framework of theoretical physics, including, for example, Maxwell's equation, quantum field theory. So as a whole, where dynamics are also derived from actions. On the other hand, if you see Einstein field equation, it is very much local. So that is why we need a local mathematics, which is differential geometry. On the other hand, this is a Lagrangian. It connects to a broader aspect of general relativity. So from here, what we see that the Einstein Hilbert action, if we take into it, is more fundamental in the sense that it generates Einstein field equations through a variational principle. On the other hand, Einstein field equation actually emphasizes on causality and dynamics. I mean to say how energy and momentum actually determines the space-time curvature, where it will be high, where it will be low. So it is basically the causality, and this is based on the variational principle. So if I take the geometry of space-time, for example this, and I zoom a particular portion, I get this kind of a structure. And from here, what I can say that the local equation, it's a very local equation, and how the dynamics help to determine the space-time structure. On the other hand, if I talk of Einstein Hilbert action, this is much more emphasizing on the symmetry and unification. That means it provides a unified way to connect general relativity to other areas, which I was just talking quantum field theory. Why? Because it uses the Lagrangian mechanics, which comes things more naturally. So from here we see that it is a global scalar function. The action formulation is critical when modifying GR, and also it encodes space-time dynamics into a single scalar action. Scalar action, why? Because it would be remaining invariant under certain changes. So this is what I can say in simple words, a little bit mathematically, what is Einstein Hilbert action. And we can summarize this into two very important statements. One is that Einstein field equations describe how space-time curves, and Einstein Hilbert action explains why the equations of space-time curvature take the form that they do. Now we come to understanding the equation, which I call it deciphering the equation. But as you will see that this equation has got different forms. Let us look into the next part of the video what the equation actually means. Now you will see that in Wikipedia, or when you go through internet, it might sound like this, or sometimes it is written as this, or sometimes it is written as this. You see that in the first equation, the C4 was omitted. In the second equation, there is a 16 pi g. And the third equation, there is both a 16 pi g and there is a Lagrangian matter, and so on. Now, all these equations are correct. All these equations are used in different areas depending upon the necessity. We will look into that later. But first, let us get a gross idea of what this equation means. So we will start with the first left-hand side, which is this S. Now this S is basically the total action, which includes contributions from geometry, that means space-time curvature, as well as the matter energy, which actually is the content of the universe. In some of the equations, to tell you that this S is divided into two parts, S symmetry and S matter. The first term is the curvature, and the S matter actually is the contribution of matter energy of the action. Totally you can say that this is the S. Then we come to this integral sign. This is a mathematical expression which combines the curvature and the proper volume element. This volume element I have written at the extreme right hand side, which I will cover up later. So what it sums up is the curvature of space-time along with the volume element, because that is the element which is moving along the space-time. Next we come to this, which is called the C4, that is the speed of light. It is raised to the fourth power because we take into 4 dimensions into account. In some equations you might not see C4. I will tell you what is the reason later. Now this 16 pi g is actually a kind of a derivation. It would be very difficult to tell it right now what this 16 pi g actually means. But this 16 pi g is actually coming from Einstein's field equation, where you will find there is an 8 pi g, and further there is a factor of 2, etc., which actually requires a derivation. So overall you can understand that this is a normalization constant, so that this equation is at par with Einstein's field equation. R, which is very simple, is a Ricci scalar, which tells how much the space-time bends. And now comes the L matter. Okay, so just to tell you, this Ricci scalar, it represents the degree to which space-time is curved, and this is actually attained by the contraction of the Ricci tensor from the Riemann curvature tensor. That would again require a derivation, which I am not going right now. Now this L matter is basically the Lagrangian of the matter. That will represent the matter field, how it interacts. Now there is, in some equations you will see there is L matter and S matter. I will come to that part later. Now here comes the most important part. There's a negative square root of minus g. This is basically called the negative determinant of the metric tensor g mu nu. I will explain to it why it is so important. Actually, this term ensures that the action is integrated over the proper volume or curved space-time. And lastly, this d for x, this is nothing but the four-dimensional volume element which is integrated over the space-time, and it is uses the infinitesimal small distance. So that is why it is called d for x. So overall, this is what it is. What we can say from this equation is that by varying this action with respect to the metric tensor g mu nu, we obtain the Einstein field equation. So the action formulation highlights the elegance and unity of general relativity as a theory of space-time, geometry and matter. So we come to the next part of our video where I'm going to explain you why this minus negative determinant of the metric tensor. So you see that the negative sign in the determinant of the metric tensor is given by this. This arises because general relativity uses the metric of space-time, which is a pseudo-Riemannian. That means it's not truly Riemannian. It uses both positive and negative, meaning it has a signature which includes both positive and negative components. Now, the metric tensor g mu nu actually describes the geometry of space-time. For general relativity, space-time has a Minkowski metric, and this Minkowski signature can be divided into two, minus plus plus plus, which is a negative sign corresponding to the time component, and plus minus minus minus. This is a positive sign corresponding to the spatial component. So overall, we can say that the signature reflects the fundamental difference between what is called time-like and space-like intervals. And further, what we see is that this determinant of the metric tensor combines all the components of g mu nu, which we just saw earlier, that it combines everything into a single scalar, scale into a pseudo-Riemannian geometry. So why again a scalar? Because it will remain invariant. So if I take a pseudo-Riemannian geometry where g is less than 0, it means that the negative determinant reflects the space-time's mixed signature. And in a pure Riemannian space or pure Riemannian geometry, it will be g will be greater than 0. So in flat Minkowski space-time, we get this kind of a derivation where you can see determinant of g mu nu is minus 1. So the negative determinant is consistent with the mixed signature of space-time. So the square root of minus g, that is the negative determinant of the metric tensor, has three important parts. One, the time-like intervals, that means motions are slower than light. We have this ds square less than 0. Then we have space-like intervals where the motion is faster than light, which is not physical as per special relativity, ds square greater than 0, and null-like intervals, which is light-like motion where we have got ds square equals to 0. So these three things become very important. Now combined with this, if you see this equation now, it has got just with square root of minus g, it has got a d for x. So minus g is accounting to the determinant of the metric tensor along with the volume element. So what we see from here is the negative sign ensures that the volume element is real and positive for pseudo-Riemannian manifolds. Now again the question is that when I say it is real and positive, you might question me, what will happen if it is negative, imaginary or negative? Obviously imaginary won't count, and if it is a negative, it is not a positive or a negative Riemannian manifold, then everything will fall. The curvature, etc., the entire physics will fall. So that is why it is important to know that it is real and positive for pseudo-Riemannian manifold. So this ensures that integration measures physical distance and volumes correctly in space-time. Coming to the volume element, which is d for x, you will see this 4 is actually the space-time has 4 dimensions, one for time and xyz for spatial components. Now, what is volume element? I have described that in my earlier lectures in General Theory of Relativity. If you can go back to my previous lectures in physics on Physics for Students channel, you will see that what is volume element it is required. So from here we get a simple understanding. D for x is equal to differential element of time x, y and z. So it is used in integrals over space-time to sum over all the conditions from all points in 4-dimensional continuum. So this is overall, but again this is not complete. I will explain it in further videos because there are certain ways, in different ways in this L matter etc. can be explained further. Now, as you see that we are deciphering this equation, this is Einstein field equation going back to Lagrangian, etc. That means there should be either a relationship or a difference between Einstein field equations and Einstein Hilbert action. This is very important for our understanding because learning certain differences will give you a better understanding. For example, when you are in dark, you know what is the difference when you are in light. So when you are in dark, you really understand the value of light. Same goes over here. The first thing I will take about is the aspect. Einstein-Hilbert action is definitely a fundamental action which is integral over the scalar curvature, and Einstein field equation actually describes something local, that is matter and energy over space-time. The purpose of Einstein-Hilbert action was to provide a variational principle for deriving Einstein field equation. This is more or less to describe the dynamics, that is locally how space-time responds to energy and matter. The formulation obviously is an integral form, and this is much more on a differential equations which is very much local in nature. So this is the definition, purpose and formulation. If I go by the mathematical nature, then Einstein-Hilbert action is an action function when minimized yields field equation. This is a second order partial differentials. Interpretation is that it encodes the gravitational interaction as an action principle, and it describes how space-time is influenced by matter and energy. Usage in physics is that this is foundation for deriving equations and exploring alternative gravity theories when we are trying to unify with quantum mechanics, but this is applied to model like gravitational effects, gravitational waves, black holes and cosmology. So from here what we can understand is that Einstein field equations and Einstein Hilbert action, what is the difference, or you can say what is the relation between that. But all is well, but question is that why do we need an Einstein-Hilbert action? I mean to say, what is the actual purpose? The Einstein field equation was good enough and it was describing nature in a perfect way. But why do we need that? Let us look into the next part of our video. Now, as you can recognize that Einstein-Hilbert action or the Einstein field equations basically describe how the distributions of energy and matters determines the curvature of space-time. So when it is determining the curvature of space-time, it is determined by the stress energy momentum tensor, that is T mu nu. On the other hand, the Einstein-Hilbert action is much more coincised. That means it becomes easier to write and derive the Einstein field equations. And by varying, okay, I will come to this later. Most importantly, it is much more elegant to write. Now, by varying the action with respect to the metric tensor, which I have just highlighted as G mu nu, we can obtain the Einstein field equations. On the other hand, this G mu nu is basically the Einstein-Hilbert action. So this is again, it is a kind of what we call a scalar function of the metric tensor, and by varying the action, if we just vary the action, we can get back to what is called the Einstein field equations. So the main idea is that to get back to Einstein field equation, to write it more easily, to take its things in a much more natural way, that is the least action principle or the action principle, we just need to modify or change the metric tensor and we can get to the Einstein field equation. So Einstein field equations are, I mean to say, they can be further extended to areas where the action principle is being obeyed. For example, electrodynamics of Maxwell equations and also quantum mechanics. In quantum mechanics, why I'm telling, because the action principle, as you know, the Feynman's path integral, the action determines the probability amplitude for different paths. So definitely the Einstein-Hilbert action allows general relativity to be incorporated into quantum field theory or frameworks. So the next thing what it comes is that there is no variation principle in Einstein field equations directly. As you can see here is that without an action, the EFE are simply postulated as simple differential equations. And the Einstein-Hilbert action allows these equations to be derived as a natural outcome of a much more deeper principle. EFE does not carry any connection to other fields because they themselves do not suggest how to integrate matter fields or quantum corrections, and the action principle incorporates the matter, that is the Lagrangian L matter, paving the way for other unified theories. Now, modern physics, as you understand, demands much more action framework. So modern theoretical physics relies heavily on the least action principle, and having an action for general relativity allows and brings better compatibility with broader structure of physics. Coming to the next question is that what does Einstein-Hilbert action achieve? I mean, so what are the things that it achieves? Let us look into the next part of our video. The Einstein-Hilbert action, from here we can go back to this, but from there it is difficult to come back. This is one part. Second is that the Einstein-Hilbert action, I would say, is a much more dynamic, and it encodes the dynamics of space-time and geometry and its interaction with matter through single scalar action. Scalar action means that it would be invariant and it would be easier to understand. Also, this would mean that the describing the specific solutions, the actions provides a global framework for governing the equations of motions for the system. On the other hand, the action approach connects general relativity to broader framework, for example, electromagnetism and quantum field theory, where dynamics are also derived from actions. If we take the variation principle, well, the delta S equals to 0, the metric tensor ultimately results into Einstein field equation, and this action approach connects general relativity to broader framework of physics. Finally, from here we can say that the Einstein-Hilbert action was not created because Einstein field equation was insufficient. Rather, it allows general relativity to be formulated in such a way that it makes it extensible and adaptable for modern and future developments. It is called action. Remember, as I was saying, it is called action, not an equation, because it is functional, that governs the dynamics of space-time through the principle of least action. So that is a kind of a quick idea, a general overview of Einstein-Hilbert action, although there are much more things to be explored, which I will do in the later part of my videos. Thank you very much for watching this video. If you have liked this video, please do not forget to subscribe and click on the bell icon to get all the notification from Physics for Students. You can like to my other channel, General Relativity Explained, and you can write to my this email ID. You can also follow on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with many other videos to keep you busy and make physics fun loving. But till then, goodbye.